Last but not least, we have the sparse abstract machine from Olivia, who is a fourth-year PhD student at Stanford, advised by Professors Kunle, Olukotun, and Kjolstad. She's broadly interested in the design of domain-specific compilers and hardware accelerator architectures with a focus on sparse applications. Olivia, take it away.
So hi everyone, my name is Olivia, and I will be talking about the sparse abstract machine, or SAM, a way to represent sparse tensor algebra as streaming data flow graphs. So similar to using systolic array accelerators in dense tensor programs, many people have been looking at sparse data flow accelerators for sparse tensor programs. And hopefully I don't need to convince you of this, since the first 4 talks in this session demonstrated this. However, we need generality because there are many different sparse computations users want to do. And unlike dense tensor programs, which reduces mainly to matrix multiplication, sparse tensor programs cannot in general do this without a huge performance hit. Therefore, the current obstacles with a fully general sparse tensor algebra system over its dense counterpart is mainly attributed to the large space of computation. For a fully general system, this includes the long tail of expressions or algorithms that you would want to compute, the backend specific or optimizing transformations, also known as schedules, the various compression formats, which I don't show here, and also, additionally, further complexity in the number of prior work backends that exist and future backends that we will develop. This large space motivates the need for a compiler. And to further demonstrate the importance of a general system that can handle arbitrary schedules, let's look at kernel fusion and data flow orderings. So my first example is SDDMM, or sample dense matrix multiplication, a kernel used in many machine learning applications. I show SDDMM unfused, which means that we will first do the dense matrix multiplication, store that into a dense tensor, and then sample it using the sparse B matrix. And I also show it fused, the performance fused, which is actually computing the kernel fully fused. And we show that this can lead to over an order of magnitude performance difference. Likewise, for different data flow orderings, I show sparse matrix multiplication, along with all 6 data flow orderings. And depending on the data, this can lead to about a 2 orders of magnitude performance difference. So what this means really is that the compilation system and data flow model needs to handle fusion and arbitrary data flow orderings, or an architect really needs to search the schedule space for their data before hardening their architecture to a fixed function accelerator. And then although I already motivate the need for a compiler, what we really want is a compiler with a clean abstraction interface, or compiler intermediate representation. And really, as LLVM-IR and ISAs have shown previously, this will lead to a clean, unified, and simpler design for the rest of the system. Because this allows the compiler design to be decoupled from the various backend implementations and parallel iteration of both. So therefore, we propose the sparse abstract machine, or SAM. SAM is an abstract machine, so that means it has infinite resources, and we assume ideal memories and ideal computation, so that we can decouple it from the hardware implementations. The surrounding SAM system includes a front-end compiler custard that uses high-level languages from prior work Taco, but it's native for an end user to describe. And additionally, SAM can bind to a cycle approximate functional simulator, which we provide in our work. And SAM can actually, a single SAM graph can harden to a fixed function accelerator design. And finally, SAM can also be used to compile and program to reconfigurable architectures, like reconfigurable data flow architectures, as well as coarse-grained reconfigurable arrays, or CGRAs. So really, since SAM is an abstract machine, what is needed to represent data flow hardware? Well, we do it through 2 mechanisms. The first one is wires carrying data through streams, and the second one is hardware modules that compute on those data through primitives. Now I will give the details of the SAM stream representation. So SAM must represent multi-dimensional tensors, including higher order ones, as various flattened streams that are more suitable for and mappable to data flow hardware. For this example, there's one coordinate stream per dimension plus a value stream at the end. So in total, for a two-dimensional matrix, we have 3 streams. The streams also contain control tokens to maintain dynamic data shape. And the tensor streams can be written back as arrays in memory and read from arrays in memory. And now a more detailed view of the SAM primitives to perform the computation. So SAM primitives are cleanly defined interfaces for each feature of sparse tensor algebra. And we're going to show kind of the 5 overall features of sparse tensor algebra. The first one is iteration through multiple tensors, which is done in SAM by composing level scanners. The next feature is combining multiple tensors together or merging streams through intersection and union primitives. The third one is repeating operands over other operands. This is the same as array broadcasting, done through the repeater primitive. And also, we need to compute scalar and reduction operators on the tensor values. And finally, we need to assign multidimensional tensor results back. And these are really the only 5 features you need for sparse tensor algebra. That's it. So since our abstract machine can handle many algorithms and many schedules, it is most similar to prior work on reconfigurable sparse architectures. However, prior work is missing higher order data representations, may not support unions and additions, and can be limited to pseudo-sparse, which is actually a dense iteration, so it can't handle hypersparse data. But coming back to the details of SAM, now that I've hopefully explained and convinced you that SAM is more general, let me give you a vector scaling example to show how the primitives and streams interact together. So this is a vector scaling example with vector b, and each 0 element of b is denoted in gray. So given a SAM level scanner, each non-zero coordinate of the vector b is emitted as a stream by the level scanner, shown on the right. And the stop tokens denote the end of the vector. Additionally, the done tokens denote the end of the entire stream. Now, the scaling of the vector by a scalar c is done via a repeater block, which dynamically repeats the scalar's reference over the vector for each dynamic non-empty element of the vector b, with again the control tokens denoting the end of the broadcasted c scalar value. And these references and coordinates are then used to compute the final result. So that now that you have a sense of kind of how SAM graphs work, I'm going to finally show how SAM primitives can compose together to compute entire tensor algebra expressions. Here I show a full graph for sparse-matrix multiplication for the row product or linear combination of rows algorithm. The details are not so important here, but what we really want to note is that the graph can be partitioned into 3 main parts: the input iteration and stream merging, the computation, and finally, the result tensor construction. And as you can see, the most important part of sparse computation is really about combining the metadata to figure out what you actually need to compute. And then, as mentioned previously, SAM is abstract, but SAM can still be used to model real-world finite hardware. In our SAM cycle approximate functional simulator, we take in architecture-specific information like bandwidth and latency numbers, along with memory hierarchy numbers to model non-ideal memory timings. And we can use SAM then to sequence our tiles, which really means merging or intersecting at a tile level. And finally, also to use SAM to model the lowest level compute graph on your processing element. And with prior work extensor's architectural configuration, we're really able to recreate evaluation from the original authors. So what this means is that SAM can be used as a simulator to explore architectural and scheduling design decisions, and can be used to compare these decisions for the sparse data that you have, in addition to the previously mentioned compiler. So in summary, We present SAM, a representation, model, and compiler intermediate representation for sparse tensor algebra as streaming data flow. We hope that SAM will improve future sparse accelerator usability, and this is through our sparse compiler and SAM representation that can target your hardware, so both prior work and in the future. And also, we hope that SAM will improve future sparse accelerator microarchitectural designs, because it can really be used as a design space exploration tool when you're building your future hardware. And finally, something far-reaching in the future, we would like SAM to inspire the development of abstract machines for other application domains for hardware accelerators as well. Thank you. Are there any questions?